Hello everyone, and welcome to this video lecture in which I will explain to you how to deal with free vibrations of multi-degree of freedom systems. So as this standard example, I again use the double mass spring system, and what we need for determining the free vibration response is first of all the equation of motion. So let me write that one down again. We have the mass matrix, which is 1, 0, 0, 1. Then we have the accelerations. Then the stiffness matrix, which was 2, minus 1, minus 1, 2, times the vector of coordinates. And the right-hand side was 0. Now, free vibration response is the response to initial conditions. So now we also need these initial conditions. And because we have 2 degrees of freedom, there will be 4 initial conditions. We have the initial deflection of coordinate 1. We have the initial deflection of coordinate 2. Let me denote that by x2, 0. And we also have 2 initial velocities. So x1 dot at 0 is x1, 0 dot, and x2 dot at 0 is denoted by x2, 0 dot, like this. What we also need is the expressions for the natural frequencies and modes. So this is what we derived in the last lecture. We found that the first natural frequency was equal to the square root of k over m. And the corresponding mode, let me just use a shorthand notation of u1, that it was alpha 1, some arbitrary scaling, times 1, 1. And the second natural frequency, omega 2, was, I wanted to write down the factor already. That was 3k over m under a square root. And the second mode was arbitrary scaling times 1 minus 1. Okay, so what I will first do is establish the general solution. For x1 and x2 together. And they can be expressed in terms of these mode shapes, and then vibration in terms of with a frequency equal to the natural frequency. So whenever the system vibrates in the first natural frequency, it will do so in the first mode. So we can write this as follows. We have the first mode, 1, 1, times C1 cosine omega 1t plus C2 sine omega 2t. Closing bracket. And then for the second mode, we have 1 minus 1. And then we allow for vibration in the second frequency, C3 cosine omega 2t plus C4 sine of omega 2t. Like this. And because C1, C2, C3, C4 are still undetermined coefficients, unknown, I basically include in these coefficients the unknown coefficients, the arbitrary coefficients, alpha 1 and alpha 2. So these are, let's say, combined to these new coefficients. So we see 4 unknown coefficients. Luckily, we also have 4 initial conditions from which we can determine them. So let's see if we have x1 at 0, and this should be equal to x1, 0. Let's substitute 0 in this expression. Then we get C1 plus C3. All right. And the initial position for 2 was x2, 0. So that is then C1 minus C3. Okay, so these are in fact 2 equations for C1 and C3. We can solve them. You can do this quickly by adding both equations, because then C3 cancels, and dividing by 2. And in this way we find that C1 is equal to x1, 0 plus x2, 0 divided by 2. So that's basically the average. And if we do it the other way around, if we subtract both equations, then we find C3 to be equal to x1, 0 minus x2, 0 divided by 2. Okay, and then for the velocities we do something similar. We need an expression for the velocities. Differentiation of the general solution with respect to time. So, oh, I see a mistake, by the way. I apologize for that. This should be omega 1. Omega 1t. That must have been confusing. I'm so sorry. So this omega 1 and omega 2 will come in front twice. So we have x1 dot at 0. That is x1, 0 dot. This is then C2 times omega 1 plus C4 times omega 2. And for the initial velocity of mass 2, x2, 0 dot, that is C2 times omega 1 minus C4 times omega 2. And here we can do the similar trick. If we add both equations and divide by 2 and omega 1, we have solved for C2. So C2 is x1, 0 dot plus x2, 0 dot divided by 2 omega 1. And C4 is obtained by subtracting both equations. And that is then x1 dot 0 minus x2, 0 dot divided by 2 omega 2. Great. So in general we see that we have two sets of two equations for two unknowns from which these four unknown coefficients can be solved. And that makes now the total solution. So let me write that down. The solution for x1 and x2 as a function of time is this first mode, 1, 1, times x1, 0 plus x2, 0 divided by 2 times the cosine of omega 1t plus x1, 0 dot plus x2, 0 dot divided by 2 omega 1 times the sine of omega 1t plus 1 minus 1 times x1, 0 minus x2, 0 divided by 2 cosine of omega 2t plus x1, 0 dot minus x2, 0 dot divided by 2 omega 2 times the sine of omega 2t. Like this. So this is the total solution of the free vibration response. And I would like to emphasize that if we have more than 2 degrees of freedom, the system, the procedure with which we solve this is the same. We just keep on adding mode shape, natural mode, times vibration in that corresponding natural frequency. Now what we see here is that if we give the system arbitrary initial excitations, the response will contain oscillations in omega 1 and omega 2. Both will be there. But if we give the system an initial excitation exactly matching one of the two modes, only that mode will appear. As an example, let's do it like this. Example, let's say that we release the system from rest, so no initial velocities, and that x1, 0 equals x2, 0. Let's say it is just equal to x0. So we give both masses the same initial deflection. In this case, x1, 0 plus x2, 0 divided by 2 is just x0. So this term with the cosine omega 1t will have an excitation, an amplitude of x0. Whereas x10 minus x20 divided by 2 will be 0. So the term with cosine omega 2 will not be there. So in this case, we will only see mode 2. Only mode 1 vibrating in omega 1. So you see that this excitation matches mode 1, and as a consequence we will only see mode 1 in the response. Now the same holds for mode 2. If we would have given them opposite excitation, so if we would have done something like this, we would see only mode 2. Only mode 2. So what we should learn from this, so first of all the solution approach, how to arrive at this solution. And then we should understand that in general we see all frequencies and all modes, and only in the specific case that we excite the system such that we only excite one mode, we will only see that one particular mode. Alright, I think this was everything I wanted to say about free vibrations. In the next video I will come back to how to deal with forced vibrations. Thanks for watching.